Title of the module: Problems. In order to get firm grip and clear idea about the topics discussed in the previous sessions, we shall do some problems in details. In this section, we shall specifically focus on the topics including polar representation of complex numbers, nth root of unity, De Moivre's theorem, subspace and rank and eigenvalue and eigenvectors in detail. Let us see some problems. The first problem shows that how to convert the rectangular or Cartesian coordinate into polar coordinate. Let us see. The first problem, we are going to convert the rectangular or Cartesian coordinate 4, 4 into polar coordinate. So, for that, first we have taken this 4, 4 as x, y, ordered pair of x, y equal to 4, 4. We know that why we are going to take this x, y, because every complex number can be represented as a ordered pair. So, z equal to x plus iy is a complex number, can be expressed as a ordered pair x, y. So, to obtain the polar radius of the point 4, 4, we can use the formula here. R indicates polar radius and R equal to square root of a square plus x square plus y square. See here, the value of x is 4 here and y is 4 here. Therefore, R equal to square root of x square plus y square equal to 4 square plus 4 square. So, 4 square is 16 plus 16 equal to square root of 32, that is square root of 16 into 2, and this is nothing but 4 root 2, that is the polar radius is 4 root 2. And next we are going to evaluate the polar argument of the point 4, 4, that is theta or nothing but t. So, t equal to tan inverse of y by x. So, here also tan inverse of the value of y is 4 and x is 4. Therefore, tan inverse of 4 by 4, this is nothing but 4 by 4 equal to 1. Therefore, tan inverse of 1. Now, t equal to, so tan inverse of y means theta equal to, that t equal to pi by 4. Therefore, the polar argument of the point 4, 4 is pi by 4. Now, we are representing polar coordinates as r, t. This r indicates polar radius, this t indicates polar argument. Therefore, r, t represents polar coordinates of the point 4, 4. So, for the point 4, 4, the polar coordinates are, what is the value of r? R is 4 root 2 and t is pi by 4. Therefore, the polar coordinates of the point 4, 4 is nothing but 4 root 2 pi by 4. So, similarly, you can represent any point in this polar coordinate form. Okay. And this problem, second problem, we are going to find out the third roots of the complex number z equal to 2 plus 2i. So, we can represent this 2 plus 2i as an ordered pair, that is nothing but 2, 2. So, 2, 2 is we have taken x, y. As in the previous problem, we are going to evaluate polar radius, are going to find polar radius and polar argument. The first one, polar radius, that is r equal to square root of x square plus y square. Here x is 2, therefore 2 square, y value is 2, therefore 2 square, therefore root 8. Root 8 is nothing but 4 times 2 and this is nothing but 2 root 2. Therefore, r, that is the polar radius is 2 root 2 and the polar argument t equal to tan inverse y by x, tan inverse of 2 by 2, that is tan inverse of 1. Again, as in the first problem, this value is pi by 4. So, in this problem, we have find out the polar radius and polar argument first. Now, we are going to express this as a polar coordinate form. Therefore, the polar form of a complex number z equal to 2 plus 2i, that is 2, 2 is, we know that the polar form. What is the polar form here? R, in general we can write r times r cos theta plus I sin theta. Here instead of theta we can use t. Therefore, this as r cos t plus I sin t. Okay. Therefore, this is the value of r 2 root 2 and t value is pi by 4. Therefore, cos pi by 4 plus I sin by 4. So, this is the polar form of a complex number z equal to 2 plus 2i. Okay. We have written the polar radius, the polar argument as well as the polar form of a complex number. So, but our ultimate aim is to find the third root of the complex number. So, to find the third root of the complex number z equal to z plus 2i, we can use the formula zk equal to 2 root 2 the power 1 by 3. Because we are identify or we are going to calculate the third root. Nth root means we can put 1 by n, and here third root we can put 1 by 3, and the general formula is cos 2k pi plus 5 by 4 by 3 plus I into sin 2k pi plus pi by 4 into 3. Here k varies from 0, 1, 2. So, by De Morgan's theorem, this is as usual. By De Morgan's theorem we can write this. We can supply k equal to 0, k equal to 1 and k equal to 2. Immediately we can get the third roots of the complex number z equal to 2 plus 2i. So, first we can supply the value k equal to 0. So, k equal to 0 means z naught 2 root 2 to the power 1 by 3 cos k equal to 0. So, 2k pi, the value is 0, okay. Therefore, pi by 4 by 3 plus I sin pi by 4 by 3. So, k equal to 0 we can write it. And this quantity remains the same, and here pi by 4 divided by 3 gives pi by cos pi by 12. Here pi by 4 into 3 equal to pi by 12. There also sin pi by 12. So, this is the value of z naught, that is k equal to 0 we can find z naught, that value is 2 root 2 power 1 by 3 and cos pi by 2 plus I sin pi by 2 in general. And we can supply k equal to 1. So, z1 equal to 2 root the power 1 by 3. Here instead of k we can supply the value 1, that is 2 pi plus pi by 4. So, 2 pi plus pi by 4 plus I sin 2 pi plus pi by 4, this is nothing but 8 pi by 4, and this 4 8 pi plus pi, plus therefore this is 9 pi by 4 and 4 into 3 12, therefore cos 9 pi by 12 plus I sin 9 pi by 12. So, z1 implies, we can simplify this one also, because 9 pi by 12 here 12. So, we can cancel because the common multiple is 3. We can cancel 3 from both numerator and the denominator. So, we can get 3 pi by 4 and plus I into sin 3 pi by 4. So, z1 equal to 2 root 2 power 1 by 3 cos 3 by 4. This is another root. And the last root we can supply k equal to 2. This first value there is no change, 2 root 2 the power 1 by 3 cos of k equal to 2 means this is 4 by. Therefore, 4 pi plus pi by 4 plus I sin 4 pi plus pi by 4. Now, we are taking LCM here, see here this is 16 pi plus pi, that is 17 pi. 17 pi by 4 by 3 plus I sin 17 pi by 4 by 3, this becomes 17 pi by 12 plus I into sin 17 pi by 12. So, this is the value of z2. So, I can set k equal to 0, k equal to 1 and k equal to 2. I have identified the third roots of a complex number z equal to 2 plus 2i by De Morgan's theorem. The roots are z0, z1, z2. So, similarly, we can give any complex number. We can write the complex number in the form of polar form by identifying the polar radius and polar the first one is polar radius and polar coordinates, and you can write a polar form of a complex number. Afterwards, by using De Morgan's theorem, we can calculate the any roots. Here they have asking the third roots of a complex number. We can identify the roots as per the given format. Now, this problem shows that the compute the value of 2 plus 2a to the power 100. So, see the 2 plus 2a problem we have discussed in problem 2. Now, we are going to take the value we have identified in problem 2 here. So, 2 plus 2i can be written as 2 root 2 cos pi by 4 plus I sin by 4. Already we have given in problem 2. So, by using this we can write z equal to 2 root 2. By De Morgan's theorem we can apply, you know that the De Morgan's theorem cos theta plus sin theta to the power n equal to cos n theta plus I sin theta. In here I have taken theta st. So, you can apply instead of theta you can take t. So, here 2 plus 2i to the power 100 can be written as 2 root 2 to the power 100, and cos, by using this theorem we can supply the value of 100 here. Therefore, pi by 4 into 100 plus I sin pi by 4 into 100. So, this can be splitted into 2 to the power 100 and root 2 to the power 100, and 4 and 100 will be cancelled. The value becomes cos 25 pi plus I sin 25 pi. So, 2 to the power 100 and root 2 to the power 100 is nothing but 2 to the power 50, and here cos 25 pi plus I sin 25 pi. So, we have evaluated the value of 2 plus 2i to the power 100 equal to 2 to the power 50 into cos 25 pi plus I sin 25 pi. Simply we can identify the polar form and you can apply De Morgan's theorem and identify find out the value of 2 to the power 2i to the power 100. You can make any power with the use of De Morgan's theorem. And the fourth one, this is another example in composition of functions. There are two functions, one is f is a function from R to R and g is a function from R to R. Both the functions have say domain and codomain. And f is defined by take x, f of x equal to x square plus 1 and g of x equal to x. This is the usual routine to find out the value of f composite f as well as f composite g. Okay, composite you can define because you know that once you can calculate the value of composite, the domain, because whenever f is a function from one domain to another one and that domain and that codomain to another domain, we can start the function another function, then only we can define the composite of function. Here both domain and codomain are same, therefore there is no need to check whether the functions are defined correctly or not. This is easily because all the one are same only. So, we can easily calculate f composite of n f composite g. So, f composite g f of x for any value x in R we can written as f of x. But f of x value is x square plus 1. Therefore, f of x square plus 1. What is f of x? F of x equal to x square plus 1. F of x square plus 1 is nothing but x square plus 1 the whole square plus 1. So, x square plus 1 the whole square as per the definition of a plus b the whole square is x power 4 plus 2x square plus 1 plus 1. Therefore, x power 4 plus 2x square plus 2. So, this is nothing but f composite f. And now we are going to evaluate the value of f composite g of x. So, this is nothing but f of g of x. As per the definition, g of x equal to x. Therefore, this is nothing but f of x. This is equal to x square plus 1. So, f composite g of x is nothing but the same as f of x in this example. So, we have identified f composite f and f composite g here. Let us another interesting example by Euclidean algorithm as well as a division Euclidean algorithm as well as a division algorithm. We are going to evaluate the GCD of 17 and 271 and express it as a linear combination of 17 and 271. First, you have to calculate the GCD of 17 and 271. Then, we can express this GCD as a linear combination of 17 and 271. There are two parts given here. By division algorithm in Euclidean algorithm, you can write 271 as 15 into 17 and the remainder is 16. So, this is the division algorithm. Now, we are going to express this 17 as in terms of 16. So, 271 in terms of 17 and 17 in terms of 16. Now, 17 equal to 1 into 16 plus 1 and 16 again in terms of 1, that is 16 into 1 plus 0. So, see here, this is the by Euclidean algorithm, this is the GCD. Therefore, GCD of 17 and 271 is 1. So, the ultimate proof is 17 and 271, there is no common factor except 1. Therefore, the GCD of 17 and 271 is 1. The second part is you can express 1 as a linear combination of, because 1 is the GCD. So, first you have to evaluate the GCD, then express the GCD in terms of the given numbers. So, to express 1 as a linear combination of 17 and 271 by successively eliminate 16, because this you are going to eliminate 16 successively, we can get the value of GCD. So, first maybe the reverse process, first 1 can be written as 17 minus 1 into 16, okay. Then 17 minus this 1 into 16, again we can written as 1 into 271 minus 15 into 16, this one. I can simply take this one also, 16 equal to 271 minus 15 into 17, okay. I have used this one. Again this 17, this we can regroup this one as 16 into 17 minus 1 into 271. So, 1 is a linear combination of 16 into 17 into 1 into 271. So, I have expressed the number, that is GCD, as a linear combination of 17 and 271. I think I have a clear idea about this division algorithm. And finally, we are going to calculate or compute 2200 cube mod 4, the value of this 2022 cube mod 4. So, we can write to the 2022 is concurrent to 2 mod 4. We can easily check. We can divide this by 4 and we can get the remainder 2. So, we can write 2022 concurrent to 2 mod 4. You can square this. Okay, 2022, so this is whole square. Therefore, 2022 the whole square equal to 2 square mod 4. We can cube. So, 2022 cube is concurrent to 2 cube mod 4. What is 2 cube? 2 cube is nothing but 8. Therefore, 2020 cube concurrent to 8 mod 4. The ultimate aim is 2020 cube mod 4 is 0. So, the value is 0. So, we can calculate it at these values. Let us see another example in detail. Okay, let us see some more problems. The first problem, the function t from R to R, that is real number to real number, is defined by t of x equal to 100x. Say x is an element of R and t of x is defined by t of x equal to 100x. We are going to verify this t is a linear transformation or not. So, if we say t is a linear transformation, we have to verify t holds additive as well as homogeneous. We are going to check two properties. The one thing is additive and another thing is homogeneous under t. The first one is, if two elements x and y belongs to R, now t of x plus y can be written as, see, as per definition, t of x equal to 100x. T of x plus y equal to 100 times x plus y. So, because 100 is a number, we can multiply by 100 here. Therefore, 100x plus 100y, which is equal to 100x means t of x, 100y means t of y. So, additive hold, that means t of x plus y equal to t of x plus t of y. The next one is homogeneous. I have a scalar r, t of rx equal to 100 times rx, because instead of x we can apply rx here. So, 100 times rx, r is a scalar, therefore, we can take outside this equal to r times 100x. So, which is equal to r times, what is 100x? This is t of x. Therefore, r times t of x. So, t satisfies the additive property as well as homogeneous property. If a transformation satisfies additive property as well as homogeneous property, this transformation is called linear transformation. So, our given t from R to R by t of x equal to 100x is a linear transformation. Now, we are going to solve the given system using augmented matrix concept. So, there are three equations, 2x1 minus 4x2 plus 2x3 equal to 0. Here x2 minus 4x3 equal to 5 and third one minus 4x1 plus 5x2 plus 9x3 equal to minus 16. This is the given system of equation. We are going to solve this using augmented matrix. So, first we have to write the augmented matrix and convert this into either a row echelon form or column echelon form. So, here we are going to convert this into row echelon form, and in this row echelon form we have calculated the solution of x1, x2 as well as x3. So, this is a procedure. First we are going to write the augmented matrix. So, the augmented matrix is nothing but the simple condensation only. The first value 2 minus 4 2 and this value also here, and here the coefficient of x1 is 0, coefficient of x2 equal to 1, coefficient of x3 equal to minus 4, and here minus 4, 5, 9, minus 16. So, this is the augmented matrix. Now, we are going to identify the values and we are converted into the row echelon form. So, for row echelon form we have made some operation using rows. In this first augmented matrix, we are convert R3 into R3 plus 2R1. That is, we can rewrite R3 as an addition of R3, that is row 3. Row 3 as, this is first row, second row, third row. So, we can rewrite third row as R3 plus 2 times R1. That is, we can multiply the entries of R1 by 2 times. and add the entries of row 3 and together which gives the R3. So, see here the first row is same, remains same, second row is remains same, the third row R3 becomes R3 plus 2R1. So, this is the first operation, we have made this. And the second one, again R3 can be rewritten as R3 plus 3 times R2, because R2 here you can multiply this entry by 3 plus again addition 3, you can get R3. So, again we have rewrite this as R3. This is the another operation. And one more operation, R2 implies R2 plus 4R3, because we have to eliminate the coefficient of x1, x2, x3. So, we are rewriting this with row echelon form with R2 implies R2 plus 4R3. So, now the augmented matrix is, here we can rewritten R2. Again see R1 is same, the entries are R1 always same. We have changed the entries of R3 as well as R2. Finally, we can come back with R1. Now, R1 can be replaced with minus 2 times R3 plus R1. So, I can multiply the entries of third row by minus 2 and add with R1, we can get R1. So, here we are going to eliminate the coefficient of x3. So, this is the augmented matrix. And another operation R1 equal to 4R2 plus R1. Here also we can multiply the entries of R2 by 4 plus addition of R1, we can get R1. So, here we are going to eliminate the coefficient of x2. So, what is the purpose of this? Means we get a triangular matrix here. So, here 2 is alone remain, therefore, we can rewrite R1 implies R1 by 2, that is the first row entries can be divided by 2, you can get 1 0 0 0 1 0 0 0 1. You no need to bother about this, because these all are the values. We can check it into triangular matrix and we can convert it into the triangular matrix, augmented matrix into a triangular matrix. The remaining values will be the solution of the systems. So, see the first value x1 and the second value x2 and the third value is x3, that is 3 1 minus 1 is the solution of the given system. What we have done here, first we can written the augmented matrix, then we can convert the augmented matrix into triangular matrix by using row operations, that is row echelon form. Finally, we got a triangular matrix, the remaining entries are the solution of the system. So, we got the solution of this system. This problem 9, find the coordinate vector 2, 2 related to the subspace spanned by 1, 1 and 1, 0. So, we are going to calculate the coordinate vector of 2, 2 in terms of subspace. Here, we have write H as span of 1, 1 and 1, 0. They have given this vector is spanned by 1, 1 and 1, 0. So, we have took that as H. Now, 2, 2 can be written as a linear combination of these two vectors. That means A times, we do not know what is the value of A. We are going to evaluate this. A times A 1, 1 plus B times 1, 0. So, we can multiply A here. See 1, 1 and 1, 0 they have given. So, we can written A times 1, 1 plus B times 1, 0. So, this is nothing but A, plus B, 0. Usual addition A plus B, A plus 0, that is A plus B, A. We can compare these coordinates 2, 2, A plus B, 2. The first value is A plus B and the second value is A. So, we can arrive at A equal to 2. Another one is A plus B equal to 2. A plus B equal to 2 implies B equal to 2 minus A. What is the value of A? A equal to 2, therefore 2 minus 2 equal to 0. So, finally, we get A equal to 2 and B equal to 0. So, now 2, 2 can be written as a linear combination of these two elements, that is 1, 1 and 1, 0. How? 2 times 1, 1 plus 0, 0 times 1, 0. We can check it, because 2, 2 equal to 2 times 1, 1 plus 0 times 1, 0. So, the coordinate vector of 2, 2 related to the basis, this basis is 2, 0, because A value is 2 and B value is 0. So, this is the coordinate vector. Finally, we evaluate the determinant of a matrix, determine the rank of a matrix 1, 2, 3, 1, 0 to 2, 4, 6. So, here also we couldn't find out the rank by using exhibiting the matrix, because we are converted into the reduce the matrix in row echelon form. After that, we can write the rank of a matrix in a easy way. So, first the matrix is written here. So, we can reduce into row echelon form. What is the operation here? R2 implies R2 minus R1. That is, we can write R2 in terms of R2 minus R1. So, this is the first entry remains the same. So, R2 implies R2 minus R1 means 102 can be transferred into 0, minus 2, minus 1. Again, third row elements are same. And last one is R3 implies R3 minus 2 R1. Under this operation, the matrix can be converted into 1, 2, 3 and 0, minus 2, minus 1, 0, 0, 0. So, the first non-zero entry of each row or column is denoted by the pivot. Therefore, here column 1 and column 2 are pivot column. So, pivot column indicates the rank. Here column 1 and column 2 indicates the pivot column. Therefore, the rank of this matrix is 2. Now, let us see another problem, that is problem 11. Find the eigenvalue and eigenvector of the matrix 3, 2, 0, 2. Here there is a 2 cross 2 matrix, that is I have taken as A equal to 3, 2, 0, 2. Taking the determinant value of the matrix, we can take lambda I2 minus A. I2 indicates identity matrix of a 2 cross 2 matrix. So, it gives the characteristic polynomial. So, first we are going to evaluate the characteristic polynomial of A, that is lambda I2 minus A equal to lambda times, what is the value of I2? 1, 0, 0, 1 minus A, the given matrix A is 3, 2, 0, 2. Now, it will becomes lambda 0, 0 lambda minus 3, 2, 0, 2. So, usual addition, we can written this as lambda minus 3 minus 2, 0 lambda minus 2. Now, we are going to calculate the determinant of lambda I2 minus A. So, determinant of lambda I2 minus A equal to lambda minus 3 minus 2, 0 lambda minus 2. So, it will becomes lambda minus 3 into lambda minus 2. When you equal to this equal to 0, we can get the characteristic roots or eigenvalues. Now, we can get the characteristic polynomial, that is lambda square minus 5 lambda plus 6. So, setting the characteristic polynomial equal to 0 and obtain the eigenvalues. So, the eigenvalues are lambda equal to 3 and lambda equal to 2, which are the two eigenvalues of A. Now, we find the eigenvector x corresponding to the eigenvalue lambda equal to 3 by solving 3I2 minus A into x equal to 0. Substituted the value of lambda here, lambda equal to 3, therefore 3I2 minus A into x equal to 0. So, here x is a 2 cross 2 matrix, therefore we can written 3003 minus 3202 into x1 x2 equal to 0, 0. First, usual preliminary addition in matrices and subtraction in matrices, we can get that minus 2x2 x2 equal to 0, 0. From the above, it is observed that x2 equal to 0, which implies x1 is arbitrary. Thus, the eigenvector of A corresponding to the eigenvalue lambda equal to 3 is x1 x2 equal to C times 1 0, where C is arbitrary. Similarly, find the eigenvector of x corresponding to the eigenvalue lambda equal to 2 by solving 2I2 minus A into x equal to 0. Here lambda equal to 2. Therefore, 2I2 minus A into x equal to 0 implies 2002 minus 3202 into x1 x2 equal to 00. Again the same operations, we can get minus 1 minus 2 0 0 x1 x2 equal to 00. Finally, minus x1 minus 2 x2 0 equal to 00. From the above, it can be concluded that minus x1 minus 2x2 equal to 0. Here, this is an equation with two unknowns. Therefore, by putting x1 equal to alpha, where alpha is an arbitrary number that gives x2 equal to minus alpha by 2. Hence, the eigenvector of A corresponding to the eigenvector lambda equal to 2 is x1 x2 equal to alpha minus alpha by 2. So, we can take alpha outside. So, it can be written as alpha times 1 minus 1 by 2. Here, we have discussed the problems related to polar representation of complex numbers, nth root of unity, De Moivre's theorem, subspace and rank and eigenvalue and eigenvector. I strongly believe these discussions will help you to understand the concepts eigenvalue and eigenvectors in detail. For better understanding, see the scripts and do some problems in your own. Thank you.